Hi, this is Chris, and this video continues the discussion of how to round floating point numbers. So far, all of the numbers which have been rounded have been normal numbers. This video deals with rounding subnormal numbers. When rounding normal numbers, I started with a 32-bit significand and rounded to 24 bits. This is because the type of the result was binary 32, which has a 23-bit significand field. The most significant bit of normal binary floating point numbers is assumed to be 1, so we never store the most significant bit of the significand when using the IEEE 754 binary formats. In this video, my target type is going to be the binary 16 format. So rather than rounding to a 24-bit result, I will be rounding to an 11-bit result. Let's do a quick review of binary 16 numbers. Binary 16 normal numbers have 11 bits of precision, and we only need to store 10 bits because the most significant bit is always 1. Binary 16 subnormal numbers have a maximum of 10 bits of precision. They may have as few as 1 bit of precision. Note that the maximum number of bits of precision is the same as the nsig value for the binary 16 format. Subnormal numbers only have a maximum of nsig bits of precision because their implied most significant bit is 0 rather than 1. That is, all of the non-zero bits of a subnormal number are stored explicitly, never implicitly. A subnormal number reaches its maximum number of bits of precision when the most significant bit of the significand field is 1. This case is illustrated in the current slide. This information is taken from one of my earlier videos. When the FP class module extracts the significand from a subnormal number, it normalizes the significand, that is, it shifts the significand to the left until the most significant 1 bit is in the most significant position. Then FP class corrects the exponent value, subtracting the shift amount from emin. Emin for the binary 16 format is -14, and this significand needed to be shifted 1 place to the left to be normalized, so the final exponent value is -14 minus 1, which is -15. While the significand is now stored as an 11-bit value, the extra bits are all zeros, so normalizing the number does not increase its precision. In the Verilog code, which implements multiplying two binary 16 numbers, we need to multiply two 11-bit significands, yielding a 22-bit result. Let's assume that the result is also normalized, that is, its most significant bit is 1. If the exponent of the product indicates that the number is a normal number, then we split the 22-bit product into the leading 1 bit, x bar, and y bar as follows. These definitions of x bar and y bar are wrong for subnormal numbers. For subnormal numbers, we need to add at least 1 leading 0 bit. We need to reduce the number of significant digits so x bar will be smaller. The bits which x bar loses will be added to y bar. How many leading bits we add and how many bits we take off of x bar is dependent on the exponent value. To start, I'm only going to look at subnormal numbers with exponents from -15 down to -24. The number of leading zeros we need to add is emin minus expn. The number of significant digits for the subnormal numbers is determined by nsig plus 1 minus emin plus expn. Remember, the expn value is the number's exponent before rounding. So if the exponent is -15, then we need to add 1 leading 0, and we only have 10 bits of precision. Notice that this diagram now has 23 bits because of the added leading 0. Also note, I'm using zeros written in white on a black background to denote that they are zeros I've added to the significand of the subnormal number being processed. Our new t-sig value comes from the 11 most significant bits of this diagram. While t-sig is still 11 bits wide, because we've added a leading zero, x bar has been reduced by 1 bit, and that bit is now part of y bar. Now let's redo the diagram for the exponent value -16. We need to add 2 leading zeros, and we only have 9 bits of precision. The diagram now has 24 bits. T-sig is still 11 bits wide, but the definitions of x bar and y bar have again changed. By now you should be able to see the pattern of what is happening each time we make the exponent smaller. We add one more leading zero, one more bit migrates out of x bar, causing more loss of precision, and that bit moves into y bar. This covers the range of exponents from e min -1, that is -15, down to e min minus n sig, that is -24. Now it's time to look at exponents even smaller than -24. We'll start by looking at when expn is -25. Now t-sig is all zeros. Our y bar value is now the original 22-bit significand. And because we don't have any x bits, x bar is effectively 0, so we treat x bar as an even number. What happens when expn becomes -26? One of our prepended leading zeros becomes the most significant bit of y bar. So for this exponent value, and for every smaller exponent value, the most significant bit of y bar will be 0. And the OR of the remaining bits of y bar can be obtained by ORing together all of the bits of our unrounded subnormal significand. We now have 3 cases for rounding subnormal numbers. Exponents ranging from e min -1 down to e min minus n sig, the exponent value e min minus n sig minus 1, and finally, all exponents which are even smaller. Now because we're rounding only an 11-bit t-sig value, it seems like it's time to replace p adder 24 with p adder 11. But before doing so, we have a corner case we need to deal with. What happens when roundBit is 1 and the number being rounded is the largest subnormal value? We can write this subnormal value as 1 point followed by 9 ones times 2 to the -15th power. The t-sig value for this number will be 0 followed by 10 ones. Adding 1 gives us the sum 1 followed by 10 zeros. Notice that this is an 11-bit sum. Because it's an 11-bit sum, it won't generate a carryout. Writing this 11-bit sum with its exponent, we get 1 0 point followed by 9 zeros times 2 to the -15th power. But we have 2 digits to the left of the binary point, so we need to renormalize. But previously, I have been using the carryout bit as a flag to tell us that renormalization was required. And because after rounding, the sum won't generate a carryout, we won't know to renormalize. What do? We could test the exponent value and determine if we're rounding the 10-bit significand of a subnormal number or the 11-bit significand of a normal number, and use either a 10-bit adder or an 11-bit adder as required. This could work, but we have to allocate gates and route for 2 different adders. A possible second solution would be to shift the t-sig value 1 bit left when we're rounding a subnormal number. But then what happens when we add? As you can see, roundBit is misaligned with the least significant bit for the 10-bit subnormal significand. We won't get the correct value when we round. When rounding a subnormal number, we also need to shift roundBit 1 position to the left. But how would we shift roundBit to the left? Right now, roundBit is being added to the sum via the carry-in bit. The other number being added to t-sig is 0. We could use a carry bit of 0 and construct the other addend with roundBit in the least significant bit, and then shift this addend to the left 1 bit when we're rounding a subnormal number. Code to implement this logic might look something like what you see on the screen now. This could work, but it's messy having to do this shift dynamically. For subnormal numbers, what happens if we add roundBit twice? This would move roundBit into the correct position for rounding the significand of a subnormal number. But if we add roundBit twice, don't we need a second adder? Not necessarily. Again, the adders I've been using really add together 3 numbers. The first 2 numbers being added are the 11-bit values tsig and 0. The third number being added is the carry-in bit. It's the carry-in bit which I've been using to do the rounding. I can add roundBit a second time using the addend, which is currently 0. I can use a 1-bit flag to control whether roundBit is added to tsig once or twice. The code using the 1-bit flag could look like the code which you see on your screen now. When we're rounding normal numbers, roundBit only gets added to tsig once, but roundBit will be added twice when we're rounding subnormal numbers. And we got the second addition of roundBit without allocating gates for a second adder and without dynamically deciding if the roundBit value needs to be shifted. We can finally write the rounding code to handle both normal and subnormal numbers. The first change we make to the rounding module is to add the inexact flag as an output. Then we declare the parameters which we're using in this module. Next, we can use the parameters to declare the details of values in the argument list for the module. We wrap up the declarations with the values used internally in the module. After the declarations, we add an always block. This is needed to encapsulate the conditional logic. Before moving on to the conditional logic, I have set the subnormal flag to 1. I could just as easily have set the flag to 0. But since there are 3 subnormal cases and only 1 normal case, it seems sensible to make subnormal true by default. This slide shows the logic to determine which of the 3 subnormal rounding modes we're in, or if we're rounding a normal number. For the case that the exponent is less than emin minus nsig minus 1, that is when the exponent is -26 or less, this is how we compute the values of last kept bit is odd, deciding bit is 1, remaining bits are non-zero, and tsig. Note that last kept bit is odd and deciding bit is 1 will always be false for this case, and tsig will always be 0. As noted earlier, the subnormal flag has the default value of 1, so we don't need to change the value of subnormal in this block. For the case that the exponent is equal to emin minus nsig minus 1, that is when the exponent is exactly -25, this is how we compute the values of last kept bit is odd, deciding bit is 1, remaining bits are non-zero, and tsig. Again, the value last kept bit is odd will always be false and tsig will always be 0. For subnormal exponents in the range -24 to -15, all of the values last kept bit is odd, deciding bit is 1, remaining bits are non-zero, and tsig are dynamic. This is our last case, rounding normal numbers. The calculation of last kept bit is odd, deciding bit is 1, remaining bits are non-zero, and tsig is identical to how they were calculated in the code which converts 32-bit signed integers to binary 32 values. This should be a reminder of why I generally use parameters rather than explicit constant values. The only thing which is special here is that we need to override the default value of the subnormal flag by setting it to 0. Outside of the always block, I used the following code to compute the value of the inexact flag. In the code to convert integers to floating point values, this computation was done at a higher level in the logic. I moved this computation into the rounding module so I didn't have to duplicate the logic for computing deciding bit as 1 and remaining bits are non-zero. Having duplicate code causes code maintenance issues if we ever need to change the logic in the future. We would be at risk of not properly updating every copy of the code. We compute roundBit exactly the same way as the code for converting integers to floating point numbers. Arguably, this is duplicated code and should be moved into a reusable code block. This is the code which does the actual rounding. Notice that there's conditional logic here. At first glance, it looks like the Verilog compiler might consume resources for 4 different adders. This is the kind of situation I had been trying to solve using Verilog's if-def statements. In the comments section of an earlier video, All My Circuits pointed out that I didn't need a solution using if-def. I tested All My Circuits' advice and found that because nsig is a constant, the Verilog compiler only generates logic for the branch of the if statement which is actually true. Thanks again to All My Circuits. The next step is to use the carryout bit to adjust the rounded significand value and the exponent value as needed. This logic is identical to the rounding code for converting integers to floating point numbers. Now we need to do some special processing. Because we're rounding subnormal numbers which can have exponent values less than -24, the value of tsig can be 0. Depending on the rounding mode, the value of roundBit might also be 0. So after rounding, we might get a rounded significand which is 0. This is different from the kind of rounding behavior which was possible in the code to convert integers to floating point numbers. We need special logic to deal with this situation. If rsig, the rounded significand, is 0, then we rounded to 0. If rsig is not equal to 0, this logic clamps the output exponent value so it can't be any smaller than emin minus nsig. This behavior is different from how I handled multiplication earlier. I will go into the details of why and how I changed this logic in the FPU module in the next video. The last bit of work in the rounding module is to return the final rounded significand value. In the next video, I'll describe the changes I made to the FPU module in order to incorporate the rounding logic. I'm not releasing the improved rounding module code until I can release it with the updated version of the FPU module. The GitHub repository for the updated rounding module and the multiplication module with rounding will be released when the next video comes out, and the location of the repo will be announced at that time. Please share this video with friends and colleagues who might have an interest in this video series. Questions and comments are welcome in the comments section. If you found this video useful, please click like below. While you're at it, subscribe to the channel, then click the bell to be notified when new videos are available. Thanks.